Hi, my name is Joshua Kaplinger, and today I'm going to be giving a quick presentation on the topic of my honors thesis and research, experimental modeling of coupled mode flutter in a turbine blade. This research was done in the Fluid Structure Interactions Laboratory at the University of Massachusetts Amherst. I would like to give a special thanks to Professor Yahya Madaris-Sadeghi and Peter Boersma for their help with this research. Modern commercial wind turbines are susceptible to two main types of aeroelastic instabilities: stall-induced vibrations for stall-regulated turbines, and coupled mode flutter for pitch-regulated turbines. The current research focuses on the phenomenon of coupled mode, or classical, flutter. In coupled mode flutter, the first natural frequency, or first mode, of a turbine blade in the torsional direction couples with a higher flapwise mode. Torsional deflections are defined as twisting of the blade about its longest axis, and flapwise deflections are defined as the blade flapping up and down, perpendicular to the direction of the incoming wind. Coupled mode flutter results in the turbine blade fluttering violently with highly negative damping, meaning that the oscillations are too extreme to be compensated by any form of structural damping. Clearly, coupled mode flutter occurring in a turbine blade is a situation that should be avoided at all costs, and although it has not been observed in existing turbines, the risk continues to rise with new developments in the industry of wind energy. There are many factors that contribute to the likelihood that a wind turbine may experience classical flutter, but the main characteristics are high tip speeds, low blade stiffness, and a center of gravity that lies behind the center of lift along the length of the blade. For decades, the size of wind turbines has been constantly increasing. Furthermore, the research and development of wind farms located offshore have begun. With vastly more space and far fewer restrictions than on land, we will likely begin to see turbines with blade lengths reaching and possibly exceeding 100 meters. Longer blades come with the inherent cost of lower relative flexibility, as well as exposing their tips to higher wind speeds, and new forms of aeroelastic tailoring often place the center of gravity aft of the aerodynamic center. These factors have brought the predicted flutter speed of existing and prototype turbine blades closer and closer to their critical rated speeds. Being able to analyze coupled mode flutter in an experimental setting would enable researchers to study the behavior to a far greater extent in comparison to the existing theoretical models. However, because classical flutter risk increases with size, replicating this behavior in an environment as small and confined as a wind tunnel is a difficult task. Previous research on this topic that has taken place in the Fluid Structure Interactions Lab has used an airfoil of a uniform cross-section to model a turbine blade. Disconnected airfoil sections run the length of a thin metal spine, allowing the blade to flex while still being able to provide lift. The airfoil is placed in the wind tunnel and exposed to various wind speeds during testing. Two distance measuring lasers were pointed at a single airfoil section, which in theory could track the oscillations of the model. But, in practice, the oscillations of the model were so extreme that the lasers frequently passed through the gaps between the airfoil sections, resulting in data that was difficult to interpret. In the current research, a 6-axis force sensor has replaced the existing lasers. Both forces and moments in the x, y, and z directions were measured at steady state for a range of wind speeds. Through the use of a numeric computing program called MATLAB, the most prominent excited frequencies were found, and the lift forces were analyzed to confirm the onset of aeroelastic instability. During this testing, it was still unclear whether or not the observed oscillations were due to coupled mode flutter. The natural frequencies of the model spine were calculated numerically and through the use of finite element analysis, but another technique must be utilized to find the natural frequencies of the entire assembly. The blade was first suspended in front of a black sheet to provide a contrasting background. Using a high-speed camera, the motion of the model blade was captured after a flapwise deflection was induced. Then, a MATLAB code was used to examine each frame of the video and track the edges of the blade. With further processing, the track deflections can be used to determine the blade's flapwise natural frequencies. To track motion in the torsional direction, colored lights were added to the setup. A green light was pointed at one face of the airfoils, and a red light aimed at the other. Thus, when torsional deflections were induced, the trailing edge of the model blade was clearly defined as the split between the green and red faces. This enables not just easy visual analysis, but the ability to write a code that can differentiate between each face and lead to the calculation of the blade's torsional modes. In summary, the continuation of this research is necessary to model coupled mode flutter experimentally. The new techniques developed for tracking the motion of the model turbine blade seem promising, but further analysis and post-processing of the high-speed videos are needed to accurately determine the natural frequencies of the entire assembly and confirm the coupling of the first torsional mode and a higher flatwise mode. Further testing of the existing blade is also needed, with the current blade tracking system using the force sensor and high-speed cameras, which improves drastically on the previous laser setup.